And we'll start off this lesson with a bad cartoon. Why statisticians don't make it as waiters. Hi, sir. I normally distributed the butter on your toast this morning. See the little normal distribution there. All right, and today we'll be looking at the differences of two proportions. So I bought a 5-pound bag of M&Ms, which has a total of 2,400 pieces of candy, roughly. I checked the proportion that are green because that's my favorite color, and I randomly sample 200 M&Ms from the bag and count 36 green M&Ms. A couple weeks later, I buy another bag, and I find 16 M&Ms out of a sample of 100. So we're going to learn how we can determine if there's enough evidence that there's a difference in proportion in the two bags, that the second bag is lower in proportion for green M&Ms than the first bag. And I can actually also do confidence intervals to estimate what the difference is between the two bags. So first of all, we're going to start with our null hypothesis. And like the previous lesson, it's just going to be the difference, but instead of two means, it is two proportions, P1 and P2, instead of mu1 and mu2. Now, on the calculator, you might say P1 equals P2. So that's another way of saying P1 minus P2 equals 0. For that to happen, they both would have to be the same. Our alternate hypothesis still takes the same three forms. It's either left-tailed, where P1 minus P2 is less than 0, or P1 is less than P2. It's right-tailed, where P1 minus P2 is greater than 0, or P1 is greater than P2. Or it's two-tailed, where P1 minus P2 just isn't 0. We don't care if it's high or low, which means P1 just isn't equal to P2. We don't care which one's bigger. So for my M&M example, what is my null hypothesis? Well, I have bag 1 and bag 2. I need to assume that they have the same proportion of green M&Ms, so there's no difference in proportions. Now I'm checking to see if the first bag has a higher proportion of green than the second bag. So when I subtract those two, that would be greater than 0. Now, I could also write it in that form where P1 is greater than P2. And if I was using the calculator, that's exactly what I would choose. Our conditions for this test and the confidence interval are very similar to what we did with a one proportion sample. First of all, it should be random. State if it's assumed or given. It could be representative, and that's the main goal. Large counts. Make sure that successes and failures are both greater than or equal to 5. It should be less than 10% of the population, so the sample size should not be too huge, unless there's no replacement, in which case it doesn't matter. So for my example, random, I told you it was given. My large counts, I had 36 green and 164 not green, and 16 green and 84 not green. So both of those meet the greater than or equal to than 5 condition. And 10%, both samples are less than 10% of the M&Ms in both bags, all right? I believe they had 2,400 candies. So yeah, I'd have to have a sample bigger than 240. So it would be tempting to use the same standard error that we use for a confidence interval, but we don't do that for one sample z-test because we did have a hypothesized value for the parameter. So we can actually calculate a standard deviation for the population instead of the standard error for a sample. So how would we do this with two different proportions? Well, in theory, both proportions are the same. So let's pool. We're going to put both samples together to get our hypothetical proportion, and we call the pooled estimate for P hat. So I just add x1 and x2 and n1 and n2. Now remember, for WebAssign, we frequently use R. So basically, whoa, I have the wrong order. X1 is the number of successes. X2 is also the number of successes for sample 1 and sample 2. N1 and N2 are the sample sizes for both. And like I said before, R is frequently used instead of X on WebAssign. So I'm going to calculate the hypothetical proportion of green candies. And so I'm going to take X1 plus X2 over N1 plus N2. In this case, that'll be the 36 plus the 16 over the 200 plus 100. And I get 0.173, which makes sense. That proportion should be somewhere between the two of them. Now that we know the hypothetical proportion, we can calculate the standard deviation for the population using only p hat, not p1 or p2. However, we still have to treat the two samples separately, so we get a formula very similar to a confidence interval because of the two n values. The main differences are that it's for a standard deviation instead of a standard error, and p hat replaces both p1 and p2. So this is our formula. All right. On the bright side, most of the time you're not going to be calculating standard deviation by hand, but we'll go ahead and do it in this case here for my bags of M&Ms. So here you go. There's my p hat for both of them, and then you just see I have the different sample sizes underneath. So I get 0.1431 on top of both of those, or 0.0463. So that's my standard deviation for what's called a pooled sample. To calculate a z-score, I need to calculate the difference in the two proportions first, which is 0.02. Then I'm going to say what I found minus 0, because that's usually our z-score is our mean, or mean difference in this case, minus 0 divided by our standard deviation, and I get 0.432, which basically means it's a shaded area. If I wanted the p-value, I'd do normal CDF 0.432 to infinity, which is 0.333. So I did this whole problem by hand, and I will show you how to do it with the calculator. So with a p-value of 0.333, that's greater than any alpha we use, so we fail to reject H0. There is insufficient evidence that the true proportion of M&Ms in the second bag is less than those in the first. So let's do it the easy way with the TI-84. We're going to press Stat and Test. Scroll to number 6, which is 2-prop z-test. X1 is the number of successes in sample 1, N1 is sample size 1. X2 is the number of successes in sample 2, N2 is the sample size for the second sample. By the way, all the above must be integers or your calculator will throw up on you. You'll get an error. So make sure these are integers, not decimals. Then you're going to scroll to the appropriate alternate hypothesis. In this case, I was assuming P1 is greater than P2. And then I'll press enter and then go to calculate, press enter. And the p-value here is denoted as p. The hypothesized proportion is denoted as p hat, which you can kind of see right there. And to see the graph, you can also select draw instead of calculate, but the graph only shows the z-score and the p-value. So let's go ahead and look at an example. We have a support group who meets regularly to help people who wear the nicotine patch. And does it help to quit smoking? Group 1 wore the patch and attended a weekly meeting, and 46 of 153 successfully stopped smoking. Group 2 wore the patch but did not attend meetings. 30 of 151 successfully stopped smoking. So we're going to state the hypothesis, calculate the test statistic and the p-value, and determine what conclusion you should come to based on the evidence. So I'm going to say that the initial hypothesis is that there's no difference in the proportions. All right. Now I'm trying to see if doing the support group helps. So that means that the proportion of people who did the patch and the support group should be higher than group 2 proportion. So that difference should be positive. Now here's what I entered in the calculator. So you can see 46 and 153, 30 and 151, and there's my alternate hypothesis. Once I hit calculate here, then I get my test statistic and my p-value, which is 0.020. Because my p-value there is less than the alpha, which in this case we can say 0.05, we reject our null, which is that they're equal. There is convincing evidence that the alternate is true, that P1 is greater than P2. Let's take a look at another example where I compare attendance on a Wednesday, where I mark 76 present out of 86, and on a Friday when I mark 72 present out of 86. If these two samples are representative, how can I compare attendance rates on both of these days? So I'm just going to go ahead and create the proportion of students that are present. Now, if I go ahead and I can actually do a two-sample Z interval for P, which is to figure out what is the range of these students present. So I press Stat and Test, and instead of going to a two-prop Z test number 6 here, I go to B, which is a two-prop Z interval. So it's going to give me the range of proportions that we think would be appropriate for this. X1 is the successes in sample 1. N1 is the sample size for the first sample. X2 is the successes in sample 2. N2 is the sample size for the second sample. And remember, all of the above have to be integers. And the C level is a desired confidence level in decimal form. In this case, we're doing 95%. Then I scroll to calculate, press enter, and I'll get this output. So based on the output I got, I can interpret the confidence interval. So there is the range right there. We are 95% confident that the difference in attendance on Wednesdays is from 0.057 lower, and the reason I did lower is that says negative, and 0.150 higher, because that's positive, than attendance on Fridays. We can actually use our confidence intervals to come to conclusions about about the hypothesis as well. If our confidence interval contains 0, then it is possible that there is no difference in the two proportions. 0 is a plausible value. So based on the interval, we should fail to reject the null hypothesis. If it does not contain 0, then there is sufficient evidence to say that we should reject the null hypothesis and claim there is a difference. So all the differences are either positive or negative, implying that it is higher or lower. So what conclusion should we come to regarding the difference in attendance rates on Wednesdays and Fridays? Because our interval contains 0, we do not have sufficient evidence that there is a difference in attendance on Wednesdays and Fridays.